Good morning, sir. My name is Meghanath from Missile B section. I'm here to say about my AET techtalk topic. My topic is about the right use of Laplace transform in circuits. We can represent each of the circuit elements as an S-domain equivalent uh, circuit by Laplace transforming the voltage current equation for each element. Resistor V is equals to Ri. Inductor V is equals to SLI minus L naught. Capacitor V is equals to 1 by S of V of I plus V naught by S. In these equations, V is equals to L of V and L is equals to L of I is equals to L of I. L naught is the initial current through the inductor and V naught is the initial voltage across the capacitor. And coming to the next slide, this slide shows the summary of the S domain equivalent circuits. Here it shows the time domain and frequency domain. Circuit analysis in the S domain. Circuit analysis can be performed in the S domain by replacing each circuit element with its S domain equivalent circuit. Ohm's law in the S domain, V is equals to ZI. So circuit analysis can be performed in the S domain by replacing the circuit element with its S domain equivalent circuit. And this slide shows the applications of the Laplace transform in electric circuits. So circuit analysis in the S domain is particularly advantageous for solving transient response problems in linear clumped parameter circuits when initial conditions are known. It is also useful for problems involving multiple simultaneous mesh current or node voltage equations, because it reduces problems to algebraic rather than differential equations. And coming to the next slide, the transfer function. The transfer function is the domain relation of a circuit's output to its input. It is represented as h of s is equals to y of x of s, where y of s is the Laplace transform of the output signal and x of s is the Laplace transform of the input signal. So y of s represents the Laplace transform of the output signal, and the x of s is the Laplace transform of the input signal. And this slide shows that the transfer function in partial fraction expressions. The partial fraction expansion of the product h of s and the x of s yields a term for each pole of h of s and x of s. The h of s terms correspond to the transient component of the total response. The x of s terms correspond to the steady state component. If a circuit is driven by a unit impulse, x of t is equals to 8 of t, then the response of the circuit equals the inverse Laplace transform of the transfer function. So these 3 points are the transfer function in partial fraction expressions. So the h of s terms correspond to the transient component of the total response, and the x of s terms correspond to the steady state component. Both h of s and x of s belongs to separate transient components and steady state components. And if a circuit is driven by a unit impulse, x of t is equals to 8 of t, then the response of the circuit equals the inverse Laplace transform the transfer function. And next slide represents the transfer function of sorry, the transfer function and the convolution integral. The output of a circuit y of t can be computed by convolving the input h of t with the impulse response of the circuit h of t. So this slide represents the transfer function and convolution of the integral, where the outcome which is where the y of t can be computed by uh, convolving the input and x of t sorry y of t can be convoluted by convolving the input x of t with the impulse response of the circuit h of t. Y of t is equals to h of t into h of t is equals to 0 to L h of lambda x in h of lambda x of t minus lambda of d lambda. That is equals to x of t into h of t is equals to 0 to L h of lambda h of t minus lambda into d lambda. And this slide represents the excitation signal of x of t. And this first picture represents a general excitation signal, and the second point is approximating x of t with a series of pulses. So approximating the x of t with a series of pulses, and coming to the third point, approximating x of t with a series of impulses. The approximation of y of t. This picture shows the excitation signal of x of t, and this picture shows the approximation of y of t. And the first point is the impulse response, and the second point is summing the impulse responses. So these are the two types of x of t and y of t. And this slide shows us the transfer function and steady state sinusoidal response. To use the transfer function of a circuit to compute its steady state response to a sinusoidal source. To make the substitution, S is equals to JW for J omega in H of S and represent the resulting complex number as a magnitude and phase angle. So briefly about this slide represents the transfer function and steady state sinusoidal response. So this response is observed by the Laplace transform in the circuit. So to use the transfer function of a circuit to compute its steady state response to a sinusoidal source. To make the substitution S is equals to J omega in H of S and represent the resulting complex number as a magnitude and phase angle. These are the 2 points which we need to prove. And these are the basic formulas to use in these Laplace transform converting to, I mean, the right use of Laplace transform in using electric circuit. If x of t is equals to a cos of omega t plus psi, and h of j omega equals to h of j omega e j naught of omega. Then yss of t is equal to ah of j omega and cos omega t plus sin cos of omega t plus sin plus psi plus not plus psi naught plus psi naught of omega. Thank you, sir.